everyone, I'm Yiying Chen, and today I'm going to introduce the topic of limiting region and yield. So firstly, let's review some of the information that has been introduced on the lecture. The definition of limiting region is the first reactant that runs out during the reaction. Then we also learned the equation of the percent yield. Percent yield equals to the ratio of actual yield and theoretical yield. Then I would like to introduce the reason why theoretical yield is larger than actual yield in common situation. So firstly, the theoretical yield's definition is the maximum possible mass of a product produced in a chemical reaction. And the product here corresponds to the limiting region. So assume we do everything correctly following the steps during an experiment. The maximum amount of a product that we can expect is the theoretical yield. Therefore, the actual yield might be equal to or less than theoretical yield because there might be some product lost during the experiment. Like there might be some product left on the glass or left on the filter paper. Or the reaction may not be completed itself, so we cannot get the theoretical yield for our product in an experiment. Today, I want to introduce a real-life example of theoretical yield. A common way for people to get pure metal is to extract from ores. Titanium, as the metal of choice in airplane, is strongly demanded by humans. To get pure titanium from ores, it's necessary to go through two chemical processes, represented by two chemical equations here. And today, we are going to mainly focus on the second stage. As we get titanium tetrachloride, we need sodium as more reactive metal than titanium to react with titanium tetrachloride and extract titanium from it. For instance, we have 140 grams of sodium and 200 grams of titanium tetrachloride. Determine which is the limiting region and why. Determine the theoretical yield of titanium. And also determine the percent yield of titanium if we finally have 40 grams of titanium as product. Now I will show you the process of mine to solve this practice example. So to solve this question, we can start from getting the molar mass of sodium and titanium tetrachloride. We can just use the molar mass of sodium from the periodic table. And for titanium tetrachloride, we need to add the molar mass of titanium and 4 times the molar mass of chlorine from the periodic table. Then, since we are provided with the mass of both sodium and titanium tetrachloride in our question, we can calculate how many moles for sodium and titanium tetrachloride by multiplying the mass from the question with the reciprocal of the molar mass that we calculated previously. So, there is 6.09 moles of sodium. And for titanium tetrachloride, we will do the same by multiplying 200 grams with 1 mole over 189.67 grams. And we will get 1.054 moles of titanium tetrachloride. Since the ratio of titanium tetrachloride and sodium in the balance equation is 1:4, so by dividing the number of moles of sodium with 4, we can get 1.52 moles, which is theoretically the number of moles for titanium tetrachloride if the sodium is the limiting reagent. However, 1.52 moles is larger than 1.1 moles that we calculate for titanium tetrachloride. So the titanium tetrachloride is the limiting reagent for this question. So based on the result of limiting regions, we can calculate for the theoretical yield of the products in this reaction. So for titanium, since the ratio of titanium tetrachloride and titanium is 1:1, so the number of moles of titanium is equal to the number of moles of titanium tetrachloride. Therefore, we can calculate the mass of titanium by multiplying the number of moles with the molar mass of titanium that can be found from the periodic table. So here, we calculate there are 50.3 grams of titanium as the theoretical yield of titanium in this equation. We also need to convert the final answer to 2 because 140 grams is 2 in question. The reason why we set sodium as the excess region in this question is to reach our goal of extract titanium. So to make titanium as the limiting region, we can make sure the reaction of titanium tetrachloride is completed, and we can get titanium as much as we can, since the percent yield equals to the ratio of actual yield over theoretical yield. So in this case, we have 40 grams over 50 grams of titanium, and we will finally get 80% as our result percent yield. I'm not sure if you still remember the stimulation that we did back in October, talking about the percent yield. So the larger the percent yield is, the closer we can get to our answer. Then why people are seeking for high percent yield? So I would like to introduce 2 points here to indicate what does high percent yield means in real life. So for the case of titanium, since titanium is widely used in our real life, and also it is not that common to get as water or other chemical product. So the purpose of us to have high percent yield is to save rare material that is not that easy to get in our real life. By completing the complete reaction with them, we can get the possible maximum amount of the product as we wish. Then for the industrial purpose, the higher the percentage yield we get, the more economic and more eco-friendly we are for this process. Here is an example of limestone, and we will extract calcium oxide from it. And the calcium oxide here is used to remove exit gases from the smokestacks. So for the company who produce calcium oxide, they need to purchase limestone. And more limestone they purchase, it will cost them more. So they have to make the best use of every limestone. Therefore, the higher percent yield they can get from this chemical reaction, they can get more calcium oxide from the same amount of limestone. And also, if limestone is completely reacted, there will be less waste in industry for the same process, so it's more eco-friendly. Then how can we improve yield in experiment? So here are some tips. During the setup, we can examine all equipment before starting a lab carefully to make sure they are clean and dry. Then we can weigh the reactant as precisely as we can. An analytical balance like this may be a good choice. And during the reaction, we can add solution drop by drop if it's necessary. A dispense set introduced in the previous lab might also be a good choice to reach this purpose. Also, we need to pay attention to conditions like temperature and pressure during the reaction, so we can make sure the reaction will go well and properly. So to summarize, today we firstly reviewed the definition of limiting region and the equation of theoretical yield that has been introduced in the lecture. Then I also introduced some reasons for actual yield being smaller than the theoretical yield. I raised total 2 real-life examples and the importance of using access regions, like its economic and eco-friendly meaning in industry. And lastly, I show some tips that we can improve our yield in an experiment. Thank you so much for listening and wish you have a good day.